Hey, welcome back. So we are at the end of chapter 7 here, and we're going to be dealing with improper integrals. I'd like to take us back to, if you recall, the fundamental theorem of calculus. The very first premise is that we have to have, including the endpoints, a continuous function from A to B. And in this case, we do not have an endpoint with infinity, which makes this what we call an improper integral. And infinity, we still have to deal with in mathematics, including boundaries and things like that. So how do we include an improper integral and make it a proper integral? And the way that we do that is down here, these are called type 1s when we have infinity involved, is we have to do a limit. So basically what's happening is I'm choosing a point here called t, and I'm integrating from 1 to t, in this case, it will be. And after I integrate from 1 to t and figure out what that integral is, and I'm all done, then I'm going to shove that t off to infinity. But that's after I turn it into a proper integral where we integrate from 1 to t. So the way I'm going to do that is I'm going to take the limit as t goes to infinity, and that's going to be the last thing that I do of the integral from 1 to t. 1 over x squared dx. Now we have a proper integral. It's going from a to b, 1 to t in this case, where t is a specific number. And it's continuous from 1 to t. And as we integrate this, we end up with negative 1 over x from 1 to t. And I'm going to get negative 1 over t minus negative 1 over 1. And what happens to this limit as t goes to infinity is that whole piece there goes to 0. And being extra careful, I have a minus minus, which means I end up with 1. Now, I want you to just take a step back for a second and understand what we're saying. We're saying this function here, as we find the area under the curve from 1 to infinity, that's like 100 quadrillion is not big enough. We have to go to infinity. All of that area is exactly equal to 1 square, whatever. Now, whether we're talking about probability or whatever it is that we're talking about with the area, what it represents, that is astounding that we can go to an infinity and still come up with a finite number. Now, let's flip that a little bit. Let's say that I go from 1 to 100 quadrillion. Well, it's not quite 1. It's just under 1. I need all infinity of it for it to exactly equal 1. So I hope that's messing with your mind a little. In the definition that we just did is where we use the t that I just described for you. Now, an improper integral are convergent if the corresponding limit exists and divergent if it does not. Now, I want to point out this one is convergent. If the limit went off and we ended up dividing by 0 or going up to infinity, then we would call it divergent. And we will experience several of those. So let's do our example here. Determine whether this integral is convergent or divergent. Well, what I'm going to do is rename this so that we can make it into a proper integral. So now it's a proper integral. In fact, I can even include the picture down here. So from t, again, I'm establishing that t is here, and then after I do the integral, I'm going to shove that off to infinity. So now we have a proper integral. And we don't need the absolute value anymore because 1 to infinity is all positive. As we know, the natural log of 1 is 0. So let's take ln of t for a second and what that graph is going to look like. Well, if I sneak off to the side here and recall what ln of t looks like, I guess this would be t, not x. It looks something like this. As I approach 0, it goes down to negative infinity, but as I approach infinity, y is going off to positive infinity. So this whole integral is going off to infinity. So we would call this divergent. Now, I want to compare the two. The first one that we did up here was 1 over x squared. The second one we did was 1 over x. This one converges. Specifically, it converges to 1. This one diverges. They're so closely related, even their graphs look almost exactly the same. They're not exactly the same, but they look similar. Now, as we're thinking about this, keep in mind, the exponent here was a 2. The exponent here is a 1. That's going to become relevant here in just a moment. All right, let's move on to our next example. This time we're going off to negative infinity. Well, that means we're going to have to make it into a proper integral by writing it like this. So what we're going to do is we're going to go from t, a specific number, up to 0, a specific number. So now we have a closed interval. We're going to integrate this, and then at the end, we are going to shove t off to negative infinity in this case. Now, we got to keep in mind, negative infinity is going to have different consequences in some cases than positive infinity. This looks to me like this is going to be by parts. So I'm going to let's switch colors there. Let u be x, dv is e to the x, dx, du is dx, and v is e to the x. So if I go uv, that's going to be x e to the x from t to 0 minus the integral of v du, which is e to the x dx. All right, so you can see when I put 0 in there, I'm going to get 0 because of the x. And when I put t in there, so negative t, e to the negative, e to the t, minus e to the x from t to 0. Now, negative infinity, and then this is e to the negative t. Now let's think about that just for a moment. What's going to happen is as that goes to negative infinity, that whole piece there goes to 0. And we're going to end up with a 0 times infinity situation. And I'm going to rewrite it like this. To remedy that, minus, now that becomes e to the 0, which is 1, minus e to the t. And a couple of things I want to keep in mind is what the graph of e to the x looks like. So this is y equals e to the x. And I want to point out that as x is going to negative infinity, y is going to 0. Keeping that in mind, as this goes off to negative infinity, this whole piece here is going to go to 0. 0. Here, I'm going to get infinity over infinity, which means if I do apply L'Hopital's, that's going to give me negative 1 over negative e to the negative t minus 1. And this is going to get a little confusing with all of these negatives here, but e to the negative infinity, so it's positive infinity. That goes off to, as e to the x goes off to positive infinity, y goes to positive infinity. And when the denominator goes to infinity, the whole piece goes to 0, giving us our final answer of negative 1. You may want to walk back through that one. That one's kind of filled with a lot of craziness there. All right, on to example 3. Here we have 2 infinities. Now we can see this is the actual graph of this. And what I'm going to do is I'm going to break this up. Now I'm going to notice that this thing is symmetric, which means this area here is the same as this area here. So what I'm going to do is I'm going to double, and we know it's an even function. If you put negative x in there, we just get the same function back. So what I'm going to do is I'm going to break this up initially like this. Ooh, I forgot the limit. Limit t sub 2 goes to negative infinity, integral from t sub 2 to 0, 1 plus x squared dx. And what I'm going to do is, because this is the same as that, I'm going to slap a big old 2 in front of it, do the 1 integral. Now the integral of that is inverse tangent from 0 to t. Inverse tangent of 0 is 0. However, it turns out to be fun. Is as we showed, and let's take a look at the graph of inverse tangent once again. In case you forgot. This is y equals pi over 2. This is y equals negative pi over 2. And the graph itself does this, it's asymptotic. So as the domain of inverse t goes to infinity, please note that y is going to pi over 2. So what does this give us as far as an area goes? Pi. Now, this would be considered convergent, as would be the first one. This is the example 2 here is also convergent. Now, here's what's weird. I want us to think about this. Negative infinity to positive infinity, all of the area is exactly equal to the transcendental number pi. How insane is that? That's just, I remember the first time seeing that, that just really messed with my head. And if you're wondering, why is that true? Here it is. We just proved it. Now, if you wanted to do this integral as well, you could. Be careful when you do it. You're going to get some negatives in there. And it's going to look like things are going to go to zero when in reality it doesn't. So just be extra careful. All right, so now we're going to have some fun. And I want to go back to our original two problems. This one, the exponent was a 2 and it was convergent. This one, the exponent was a 1 and it was divergent. So this begs the question, for which example, or for which values of p is the integral 1 to infinity of 1 over x to the p dx convergent? Interesting. So let's fix this up just a little. Now, p is going to be a constant, a specific number. And we haven't even specified, does it need to be an integer, or can it be a fraction or decimal and things like that? And the reality is it can be any real number. But let's actually integrate it, but we're going to treat it like it's a real number. And we have to be careful. There are 3 letters here. There's an X, there's a T, and there's a P. P is a constant, it's a specific number. And we're going to drop this into here. And 1 to any power is always 1. So I want to point out that when this exponent is positive, that limit is going to go to infinity. It'll be divergent. When that exponent is negative overall, that t is going to drop down into the denominator. And when the denominator goes to infinity, the whole thing goes to 0. So everything depends on this being positive to be convergent. If it's 0 or negative, it's going to be divergent. So let's see what that means. So in this case, P has to be I have that backwards. Let's redo that. 1 minus P has to be negative to be convergent, which means negative P, and P has to be bigger than 1. Sorry, I had that switched. To be convergent, this has to be true. So which values of P are going to make this? When P is bigger than 1. So as long as P is bigger than 1, and we can see that in our previous example. When P is 1 or less than 1, down here, then it's divergent. When P is bigger than 1, which it is, it's 2 in this case, it's convergent. That's going to be very useful. Actually, that fact all over itself will be very useful at the last chapter in the book. I'll come back to that. All right, so let's take a moment and switch gears a little and say, I'm going to integrate this. No problem. This becomes ln f(x minus 1), going from 0 to 3. When x is 3, I'm going to get ln of 2. And when x is 0, I'm going to get negative 1, but it's absolute value of negative 1. So the whole thing goes to 0. So I get ln of 2. Now here's the problem. We just did another improper integral and bowled right through the fact that 1 makes this denominator undefined. And 1 is within this integral here, the boundaries here. That's the problem. We just skipped past that, and it looks like we ended up with an answer, when in reality, this is not the way to do this. Which brings us to our second type of integration, improper integral. All right, if f is continuous from a to b, is discontinuous at b, then we're going to have to approach it from one direction. So from a to t, and then we're going to shove t off to b after we do the integral. And it goes the other way around, that we're going to shove t towards a if we have a problem at the beginning of the integral. Once again, it's considered convergent if the limit exists, and it's divergent if it does not. So let's do a few of these. All right. Now you'll note that we cannot have x cannot equal 2. If we do, we're dividing by 0, and that's no good. So we're going to have to rewrite this as the limit as x approaches 2. Now that's going to be from the positive side, meaning from the right, of the integral of, this should be t to 5 of 1 over square root x minus 2 dx. Cool. Meaning we are going to stop short right here at t, and then I'm going to shove t off to 2 to the left. All right, so let's do a quick substitution. And this becomes, and I'm going to hold off on the boundaries for now. I'm not going to convert them to u. I'm going to convert everything back to x. And so this integral is going to give me the square root of x minus 2. So that becomes 2 root u, and u again is here. And this is going to go from, I'm going to go back boundaries, t to 5. And as we look at this, we can see right away, when I plug in 2 there, I'm going to get 2 minus 2, which is 0, which is fine. We can take the square root of 0, not a big deal. Meaning this whole part right here goes to 0. So what does my answer end up being? It's convergent to 2 root 3. And so it's already written here. End up with 2 root 3, no problem. Now for number 6, we're going to run into an issue where we can see that the boundary when x equals 1 from 0 to 3, this is the one we did before, that was an improper integral. We're going to have to actually break this up into 2 pieces. And we're going to approach it from the negative side, the left side. And then we're going to try to continue piece 2 to 3. Now here's the thing. If just one of these are divergent, the whole thing's divergent. So I'm just going to focus on this one here. And what's going to happen here, when I plug in t there, that's minus. Now when I plug in 0 there, I get absolute value of -1. That's just 1. That whole thing goes to 0. And here's the problem. As we have natural log approaching in this case 0, because we're getting closer to 1. As we're approaching 0, notice what's happening. This is shooting up to -infinity. So this whole thing ends up going to -infinity. Now, because just this one part is divergent, the whole integral is divergent. All right, for our last example, we can't take the natural log of 0, so this becomes the limit as t approaches 0 from the positive side, the integral of t to 1 of ln of x dx. And I've done the integral of the natural log of x before, but I'm going to do it again anyway. I'm going to let u equal ln of x, dv is dx, du is 1 over x dx, and v is x. And we're going to end up with the limit as t approaches 0 from the positive side, uv, which is x ln of x from t to 1, minus the integral from t to 1 of x times 1 over x dx, and you can see that goes away. And we end up with limit as t approaches 0 from the positive side. I get 1 there, ln of 1 is 0. And as t approaches 0, that's going to be minus, I'm going to get 0 there times infinity. So actually, I'm going to get 0 times -infinity, which we'll deal with here in just a moment, minus, that just becomes x from t to 1. All right, so we need to deal with this. And I'm going to rewrite it as 1 of x over 1 over x. And that's going to be infinity over infinity. T to 1. And here we're going to end up with minus, that's going to be 1 minus -0. Yeah, okay, so that goes to that goes away. That part. And here I can apply L'Hopital's. And I get 1 over x over 1. And you can see that what we're getting, my bad, this is that there. And this whole piece, so this is -1, this whole piece, let's write it out. And these are t's at this point, t goes to 0 of -t minus 1. And you can see that goes to 0. Gives me, the limit is -1, which means it's convergent. I know that can get a little tricky, and there's lots of negatives in this one, so just be really careful when you study this. I hope that helped.